Welcome back, everyone. Today, we are diving deep into a landmark paper in dynamic meteorology. We are looking at J.S. Sawyer's 1956 classic published in the Proceedings of the Royal Society. It directly connects to our textbook's chapter on frontogenesis and vertical motions. Bumblebee, don't we already know how Earth fronts work from the classic Norwegian model? Warm air slides up over a wedge of cold air, creates clouds, and gives us rain. It's simple as that. What was left to solve in 1956? Ah, Cliffjumper, that is exactly what Sawyer called the problem. The Norwegian model tells us what happens, but it doesn't adequately explain why. Simple dynamical theory shows that a sloping boundary between two air masses of different densities can just sit there completely stable with zero vertical movement. Earlier theories tried to blame surface friction or turbulence, but they only accounted for a tiny fraction of what was actually going on. Sawyer's core premise is that active fronts aren't just static boundaries, they are zones of active horizontal confluence that force a vertical circulation. Okay, so you're telling me he shifted the focus from the slope itself to the wind fields around it? Precisely. Good job, Cliffjumper. Sawyer tested this idea using two distinct procedures. First, he gathered empirical data from real synoptic situations, tracing 24-hour air trajectories over 20 different active fronts near the British Isles. Okay, well, how did he track those? Well, he calculated trajectories using upper wind observations and geostrophic measurements from isobaric charts at various levels. These were from 2,000 feet all the way up to about 300 millibars. All right, so did the real world data support his idea? It's funny you say that because it did overwhelmingly a good job. In 19 out of the 20 active cases, air masses on the warm and cold sides were genuinely converging or confluent. When he looked at inactive fronts, that confluence was completely missing. He also calculated the temperature changes along these paths. He found frequent cooling on the warm side of the frontal zone and warming on the cold side. Wait, so you're saying that there was warming on the cold side because the sinking air warms adiabatically? Precisely, exactly, Cliffjumper. The cooling means that the warm air is rising, and the warming means the cold air is sinking. This provided direct synoptic evidence that an active vertical circulation was in progress. Now, for the second procedure, the math. Sawyer treated the atmosphere as a simplified incompressible fluid and set up a partial differential equation to model how a confluent wind field alters the density gradient. He solved this numerically using relaxation methods for several idealized cases. Okay, well, what did the math reveal? Did the wind field alone create enough rain? Well, it created the vertical loop, warm air up, cold air down. But here's the thing, the calculated vertical velocities from dry confluent alone were too weak to explain the moderate to heavy rainfall we see in real life. Okay, so obviously that means that something was missing. Do we know what? Well, the answer is quite simple, latent heat. When Sawyer factored in moisture and condensation, reducing the vertical stability in the cloudy air, the circulation got a massive boost. Furthermore, when the atmosphere approaches what we call neutral dynamical stability, the vertical updrafts amplify drastically, easily explaining heavy frontal lane. Okay, did his model match how fronts look on a standard weather map? Yes, remarkably well, in fact. The model showed that the temperature gradient sharpens fastest near the ground and near the tropopause, remaining weaker in the mid troposphere. That perfectly matches our synoptic observations that fronts are always best defined at the surface and aloft. Wow. So, Sawyer basically proved that frontogenesis derives the rain, not just the front itself. But Bumblebee. If I can share a lingering question, I still find it challenging to conceptualize how a model using geostrophic winds can fully dictate ageostrophic vertical circulations. If the primary flow is geostrophic balance, how does the cross-frontal ageostrophic engine initiate so cleanly without tearing up that balance? Well, that's the greatest beauty and the lingering challenge of quasi-geostrophic theories. The geostrophic wind acts to disrupt the thermal wind balance, and the ageostrophic vertical circulation is forced to step in as a restorative torque to bring the system back toward balance. It's a continuous dynamic dance. Even Sawyer noted that his simplified model couldn't capture every real world variable, especially since fronts are usually embedded in larger scale cyclogenesis systems that have their own independent updrafts. But to summarize his legacy, active fronts require active wind confluence. Without it, the front decays. With it, you get the vertical engine that gives us our weather. Well, that's all for today. Cliff Jumper, thank you for all the questions today. But make sure to review all the equations for the lab we have tomorrow.